Good morning. Today we're going to be doing lesson 11 of module 6. By the end of this lesson, you'll be able to recognize and justify that a linear model can be used to fit data. You'll know you're successful when you can interpret the slope of that linear model and answer questions to solve a problem. Okay, we're going to go ahead and get started. All right, starting with example 1, I'm going to go through this and I just want you to follow along with me. Let me know you have any questions, and then you'll do one with me for example 2, and then I'm going to try to get you guys to do one on your own, okay? It says, Old Faithful is a geyser in Yellowstone National Park. The following table offers some rough estimates of the length of an eruption in minutes and the amount of water in gallons in that eruption. Okay? Jing wants to predict the amount of water in an eruption based on the length of the eruption. What should he use as the dependent variable and why? So we have two things that we are comparing. We're comparing the length to the amount of water spewed when these geysers erupt. Which one depends on the other? Well, one thing I always want you to know is that time is always independent. Time doesn't depend on anything else. It's completely independent of everything else. It's going to, continue to work the same way it's always worked, no matter what else is going on in the world. Time is going to stay the same, right? And we've talked about that many times. So time is going to always be our independent variable. And then we just want to check and make sure that this makes sense, because then that means the amount of water in this case would be our dependent variable. So just to say it out loud, in this case, the amount of water that's spewed from a geyser depends on how long the eruption was taking place. So that makes sense here, because the longer that there's an eruption, there's going to be more water that comes out. So that's what I'm going to write down here for the dependent and independent variable. Length of time is the independent variable, or our x, and amount of water is the dependent variable. And I'll just rewrite something else down below. You do not have to write this part, but it just kind of helps clarify some things for me. The amount of water depends on the length of the eruption. That's my little explanation, okay? So this is the first step we have to complete in order to create a scatter plot, create a line of best fit, create an equation for that line of best fit, and then use that equation to make predictions. We have to know what's dependent, what's independent, because that changes how we're going to draw our graph. Okay, let's go ahead and continue on to the next page. So based on what we just found out or determined in the last slide, we want to figure out which one of these graphs actually is correct. So it says, which one of the following two scatter plots should Chang use to build his prediction model? Explain. The difference between these two is very small. This one has the length of time written right here on the side, on the y-axis. This one has it on the x. This one has the amount of water on your x. This one has the amount of water on the y. So we just want to know which one of these is correct, which one's incorrect. Remember that this is our x value down here. This is our x-axis. And this is our y-axis. Okay, so in the last slide we identified that our x value, our independent variable, was length of time, which matches this one right here. And we also identified that our y variable, our dependent variable, was amount of water. So the correct graph is the second graph. this graph is correct, or this scatter plot is correct. Because the dependent variable and independent variable are in the correct spaces. The dependent variable is on the y-axis and the independent is on the x-axis. Okay. It goes on to say, suppose that Ching believes the variables to be linearly related. Use the first and last data points in the table to create a linear prediction model. So we're going to use the first and last data points in the table to create an equation. So here is the data table that we saw in that first slide. So we're just going to use the first point and the last point to create an equation. This point and this point. Remember that the minutes is our x, length of our amount of water is our y, and we're just going to do y2 minus y1 over x2 minus x1. Okay, so my y2 value is 8,400 minus my y1 value, is 3,700 over x2, 4.5, minus x1, 1.5. Okay. 8,400 minus 3,700 is 4,700. And 4.5 minus 1.5 is 3. All right, and when we reduce that value, when we do 4,700 divided by 3, we get a number that our m equals, we're going to round it off, 1,566. And I'm just going to round it to 0.7 because it's 0.6 repeating. Okay, so this is my m value, and now I need to find my b value. Okay, so I'm going to start with this, and I'm going to start with my blank equation. Y equals mx plus b. Okay, we know that our m is this number, so I'm going to go ahead and change my m. So this now becomes y equals 1,566.7x plus b. I can choose any two numbers in my graph. I'm going to go ahead and choose this first row that I just highlighted yellow. And I'm going to change my y and my x to what those numbers actually are. So the y variable there is 3,700. So I have 3,700 equals 1,566.7 times my x value there, which was 1.5, plus b. And now I'm going to solve for this b value. First thing I want to do is multiply these two numbers together. 1,566.7 times 1.5, and I get 2,349. I keep everything else the same, keep my plus b, keep my equal sign, keep my 3,700. From there I want to get b completely by itself. Right now it has plus 2,349 beside it, so I'm going to do the opposite of that. I'm going to take away that number, and I'm going to do it to both sides. Okay. Over here it cancels, and I'm just left with b. Over here, 3,700 minus 2,349 is 1,351. Okay, so I now have my b value, and I had my m value already, so I can write my full equation in slope-intercept form. Y equals mx plus b. Okay, Okay, so y equals my m, 1,566.7, x plus b, which was 1,351. Okay, so I have now created an equation to model this relationship just using 2 points from my table. Okay, please make sure you have all this down. Let me know if you have any questions. You will have to do this on your exit ticket today. All right, we're now going to use that linear equation we came up with to answer some questions. So I'm just going to rewrite it at the top here. It was y equals 1,566.7 x plus 1,351. Okay. It says a friend of Chang's told him that Old Faithful produces about 3,000 gallons of water for every minute that it erupts. Does the linear model from part C support what Chang's friend said? So one thing I want to remind you of, we have our x and our y here. X represents minutes. Y represents the amount of gallons. Okay, and this person is saying that with 1 minute we have 3,000 gallons. This is their numbers they give us. And we want to see, does this check out? So what we're going to do is we are going to plug these x and y numbers in to our equation up here and see if it balances out. So our original equation was y equals 1,566.7 times x plus 1,351. I'm now going to be changing my y to a 1 and my y to a 3,000. That's my y value. And my x is going to be changed to a 1. All right? So my new equation becomes 3,000 equals 1,566.7 times 1 plus 1,351. And I want to see if this matches. Well, first step, 1,566.7 times 1 is just itself. So that stays the exact same. And then we're just going to be adding 1,351 to that. And I'll do that really quickly in my calculator. What I get is 2,917.7. And so this is the final part of my equation. All right. It says 3,000 equals 2,917.7. Now, that is not true, right? 3,000 does not equal that exact number. But Chang's friend said about, right? He said, yeah, I heard that this geyser, it produces about 3,000 gallons every minute. Is that true based on what we just did mathematically? Yeah. Our linear equation supports that. It is very close. So he's correct. It is about 3,000 gallons per minute. It is roughly 3,000 gallons per minute. That number is supported by our equation. Okay? We are not going to do this last part here. So just ignore that and make sure you have that information that we did up top before we move on and get some practice in. All right, so we're now going to do this one together. Number 2, it says the following table gives the times of the gold, silver, and bronze medal winners for the men's 100-meter race in seconds for the past 10 Olympic Games. So the two things that they're comparing here are the times and the years. below it says, if you wanted to describe how mean times change over the years, so we're talking about time in years, which variable would you use as the independent and which variable would you use as the dependent? So this one is a little bit trickier, and the reason why it's tricky is because we're comparing two different times. We're comparing the mean time of these races, and we're comparing the years, which is also a form of time. But one of these is going to be dependent on the other. So does the year, the actual year of the time in history, depend on how fast these people run? Or does the average time of how these people run depend on the year that it is? Well, you should have identified that the years, in terms of like our calendar history, those are never going to depend on anything else, right? Next year it's going to be 2022, no matter what. But next year, the mean time of, an Olympic race might be dependent on the year. For example, this year we didn't have the Olympics, or last year we didn't have the Olympics because of what was going on in the world, the pandemic and everything. So our X here and our Y here are going to both be time. One of them is going to be our year. One of them is going to be the time of the race that the racers run. So what is independent? What is our X? Is the year the race takes place. What is dependent on that is the mean time or the average time. Mean means average. Of race. Okay, so please make sure you have that written down before we move to the next slide. All right, here we are going to be drawing a scatter plot together based on our data. So the first thing we want to do is draw our X and Y axes. This is our X and this is our Y. Okay, we said the independent variable here was our years, and our dependent was the race time, specifically the average race time. All right, so go ahead and write that down first. For our years, we're going to start with 1976, and we're going to go to 2012, but we're going in increments of 4, so the next one would be 1980, then we have 84, 88, 92, 96, 2000, 2004, 2008, and 2012. Okay. On our y-axis, we're going to start with probably like our lowest average number that we get. I would say we start at about 9.7 average seconds. And I'm just going to go up in increments of 1, 9.8, 9.9, 10, 10.1, 10.2, and 10.3. Okay. Now we're going to place our dots on the scatter plot based on the table they gave us. For 1976, it was 10.09, which is very close to 10.1. So it's going to be right beneath 10.1. It's going to be right around here. For 1980, it was 10.30, so it was right on this line, 10.3. For 1984, 10.13, so right above 10.1. 1988, it was 9.96. I'm just going to put this right at 9.9, a little bit higher maybe. For 92, it was 10.01 again, 10.01, so this is like right at 10. For 1992, 1996, 9.88, this is very close to 9.9. For the year 2000, it was 9.97, so very close to 10. For 2004, 9.86. It's close to 9.9. 2008, 9.83. And then 2012, it is 9.72. Okay, so this is our scatter plot. Do you see any trends in this data? I definitely see a trend. I see a downward or negative, I'll say negative linear trend. Okay, as you can see, as the years have gone on, it seems like average race times have gotten shorter. People have gotten faster. Okay, so we have a negative linear trend on this graph. Let's go ahead and draw a line of best fit. I'm just going to say it probably goes like right here. Our graphs are not perfect because we drew them, so our line of best fits are not going to be perfect, but we're going to use points to find our line of best fit down below. It says one reasonable line goes through the 1992 and the 2004 data. Okay, find the equation of that line. Well, I'm going to write down our 1992 and 2004 data really quickly. So these are the two data points for 1992. The race was 10.01 average seconds, and for 2004 was 9.86. What we're going to do is we're going to find our line. We start by first finding our m, which is y2 minus y1 over x2 minus x1. In this case, our y2 value is 9.86 minus our y1 value, which is 10.01 over x2, 2004, minus x1, 1992. And now we can actually solve this out. Please do this in your calculator and check it with me in about 30 seconds. All right, for the top number, you should have got negative 0.15. And for the bottom, 2004, take away 1992 is 12. Okay? When we reduce that, we're going to do negative 0.15 divided by 12. And what this comes out to is negative 0.0125 for our m value. So we now know that our m is this. Our slope is negative 0.0125, and we already identified that our slope was negative, so it does match. From there, we need to find our b value. So we're going to be plugging this m value into our original linear equation, y equals mx plus b. So we've already identified that m is negative 0.0125, so our equation becomes y equals negative 0.0125 x plus b. All I did was change my m to what I actually found m is. From there, it doesn't matter which point I choose. I'm probably just going to choose this one right here because my numbers are smaller, and I'm going to replace my y and my x with those numbers that they give me. So the y variable here is 10.01. Keep my slope. My x variable here was 1992. And I keep my plus b. Okay. From there, I can begin to solve this. The first thing I want to do is this multiplication. 1992 times my slope, which was negative 0.0125. What I get is negative 24.9. I keep everything else the same. Okay. From there, I'm trying to get b by itself. Right now, it's being added to negative 24.9. I'm going to do the opposite of that. The opposite of adding to 24.9. Negative 24.9 is adding positive 24.9. And we do it to both sides. Over here it cancels and I'm just left with b. Over here, 24.9 plus 10.1 is exactly 35. So I now have my b value, and I found my m value already before, so I'm going to rewrite my entire equation in slope-intercept form. Y equals mx plus b. Okay, where my m is this number, my b is this number. This becomes y equals negative 0.0125x plus 35. Okay, while you're making sure you have all this written down, I'm just going to point out a few things. Remember that our y here is our dependent variable. This is the race time. This is our slope. Our x is our independent variable, which in this case is the year. And our 35 is our y-intercept. That's where this graph starts. Please make sure you have all of this down before we move on to our next screen. For this slide, we are going to answer some questions based on our line. We're not going to do part D, we're just going to do part E. It said, if this trend continues, what is the mean race time you would predict for the gold, silver, and bronze medal winners in the 2016 Olympic Games? Explain how you got this prediction. So the first thing I want to do is rewrite the equation we came up with in the last slide, which was y equals negative 0.0125x plus 35. Okay, and then we're going to plug in what they give us. They want us to find the 2016 Olympic Games. Well, if you remember from the last slide, 2016, that's the year, and our year is our x. So we're going to change that x to a 2016. So this becomes y equals negative 0.0125 times 2016 plus 35. Okay, and we're going to solve this. These two numbers, the first thing we're going to do is multiply those together. 2016 times negative 0.0125, I get negative 25.2. From there, I'm just going to do this math. Negative 25.2 plus 35. And what I get is 9.8. Okay. So my prediction is that it's going to be an average time of 9.8 seconds in 2016 based on my linear model that I came up with for my last examples. Okay, go ahead and please make sure you have this down before we move on. All right, the last bit of practice I'm going to have you do here on your own, and we're going to just kind of check it off before we move into the closure and exit ticket. So it says, from the United States Bureau of Census website, the population sizes in the United States are as follows. Okay, we have two tables, has our years and our population size. What I want you to do is tell me which of these is your independent and which is your dependent. Okay, that is your first question that I want you to answer right here. What's independent and what is dependent? I'll give you about 10 to 15 seconds to do that. Okay, just write your answer off to the side. All right, you should have identified that your year is independent. This is your x, which means your population is your y. So x, your independent variable, is the year, and your dependent variable, your y, is the population. Okay, you should have known that because time is independent always. And basically the population depends on what year it is. Okay? From there, I'm going to have you guys find your M. I know I crossed off all of these because I don't want you to do them. I want you to find your M using the formula y2 minus y1 over x2 minus x1. And these are the points that I want you to use. I want you to use, let's do 1920 or 1820, and let's do 1920. Okay, so those are the two points that I want you to use. Do y2 minus y1 over x2 minus x1, and please tell me what your M value is. I'll give you a little bit of time to do that. Alright, if you were doing y2 minus y1 over x2 minus x1, you would have written in 106.0 minus 9.6 over 1920 minus 1820. And when you do that math out, you would have received an answer that looks like this. You would have got 96.4 over 100, and when you reduce that, you should get that your final M value, your final slope is 0.964. Okay? From there, what I'm going to have you do next is find your B value. Okay? So I want you to rewrite your equation format y equals mx plus b. And I'm going to walk you through this. The first thing we're going to do is we're going to change our m to what we actually found m is, 0.964. So it becomes y equals 0.964 times x plus b. Okay? From there, I want you to change your y and your x to an actual point that they give us. And I'm just going to use, I want you to use this 1921. So you're going to be turning your y into 106, and you're going to be turning your x into 1920. And what I want you to do now on your own is isolate this variable and solve for b. Tell me what b equals. I'll give you a moment or so to do that. It's not much math here. The first thing you should have done is multiply these two numbers together, and you would have got 1,850.88. From there, you want to subtract that number from both sides to isolate your variable. Over here it cancels and you're left with a b equals negative 1,744.88. Okay? The last and final thing I want you to do here and be able to do is to take your m and your b and write out your final equation in slope-intercept form. So go ahead and change that equation that I just wrote to match this specific situation. I'll give you about a second or so to do that. All right, and this in the end should say y equals m 0.964 x plus b, which is negative 1,744.88. All right, and that is our final equation. Later we will be able to use that equation to make predictions based on values that they give us. Maybe we want to predict the population in 2040. We could use this equation to do it. Okay? We're now going to close out our lesson and then get into our exit ticket. Alright, just to close out this lesson for today, in the real world, we're given situations that have two numerical variables. We can use those variables to create scatter plots. We can use those scatter plots to create lines of best fit. We can then create an equation for that line of best fit and then use it to make predictions. Okay? That is what we did today, and that's what you're going to do in your exit ticket right now. Alright, for your exit ticket today, here's number 5. You're going to have to identify the independent and dependent variable when given a table. You're going to have to find the slope like we just did in that last one and the two previous ones. You're going to have to then find the y-intercept using that slope. And then you're going to have to use that equation that you come up with to make a prediction, okay? Go ahead and do this in Galileo right now. It is Module 6, Lesson 11, Exit Ticket. And then go ahead and do your lesson reflection, and then you can get started on some of your weekly work if you have stuff to do for that. Okay? Good luck.